Hello everyone. In this chapter we're going to talk about the Internet Control Message Protocol, or ICMP. For our objectives, we're going to explain the basics of ICMP and the roles it plays on networks. We're going to talk about the specs listed in RFC 792 that defines ICMPv4, including the header format, the different types, and various formats of ICMPv4 messages. We're going to have a basic overview of ICMPv6. We're going to look at its header format, the different types and formats of messages, and how error messages and informational message types are organized. We're going to look at the details of the different ICMPv6 error messages, including those listed as ICMPv4. Some of them have been upgraded for ICMPv6. We're going to talk about the different ICMPv6 informational messages, including those that existed under ICMPv4, that have been upgraded, or that are new for ICMPv6. We're going to talk about the general differences between ICMPv4 and v6. We're going to look at PMTU discovery and how it operates between IPv4 nodes and the involvement of the default packet MTUs, packet fragmentation, and the effect of a packet being marked for no fragmentation relative to ICMPv4 messaging. We'll discuss how PathMTU discovery has been changed for IPv6 and the associated changes to ICMPv6 messages for the new technology. We're going to talk about the various processes for testing and troubleshooting with ICMP. We're going to talk about ping and traceroute, pathping, and routing sequences and security issues. We're going to talk about the network protocol analyzer data and use data to decode both v4 and v6 packets in order to understand the version types, sequencing, and other info. So some basics about ICMP. If ICMP was a part of a mechanic's toolkit, it would be a screwdriver or a wrench. If it was part of a cook's utensils, it would be a measuring cup or a stirring spoon. It's really that basic. Without the ability to use ICMP utilities like ping and traceroute, it'd be really hard to do any maintenance work on a network, especially with any speed. Remember, ICMP is not only part of the OSI network layer, but part of the internet layer of the TCP/IP stack. So again, if you want to revisit the OSI model in the TCP/IP stack, please do. So ICMP, what does it do? It provides information about network connectivity and routing behavior. It gives you a way to return information to senders, and messages are really nothing more than specially formatted IP datagrams. And it complements the IP datagram delivery services. ICMP provides what IP itself can't: routing, reachability, and control information, as well as delivery error reports. So different roles that ICMP plays on IP networks. We have a table here with various services, but we have echo and echo reply, destination unreachable, source quench, redirect. These are the various message types that there are in ICMP. So ICMPv4, it was the core protocol in the IP suite. Originally, it was provided in RFC 777, and it was obsoleted by RFC 792. You're all probably familiar with ping. It's widely used to test the connection between two computers. And ICMPv4 supports a series of network testing and error messages. So the protocol has no payload, and it's not used by computer applications. In RFC 792, this RFC provides the basic spec for all ICMP messages. And according to this RFC, ICMP provides a mechanism for gateways or routers or destination hosts to communicate with the source. Messages take the form of specially formatted datagrams. It's required in some implementations of TCP/IP, and it reports errors about processing of non-ICMP IP datagrams. And although RFC 792 was published in 1981, it defines a primary function of and blueprints for ICMP messages to today. It's been updated by RFCs 950, 4884, 6633, and 6918. So in this section, we're going to cover each portion of the header structure for ICMPv4, the functions and the various ICMP packet types. And we're going to talk about some examples of the ICMP query and error messages that can be found on a network. So value 1 in IP header protocol field denotes that an ICMP header follows the IP header. The ICMP header portions are the constant portion and the variable portion. Here is an example of an ICMPv4 header. So the constant ICMP fields, ICMP packets contain 3 required fields after the IP header: the type, the code, and the checksum. The type field identifies the types of ICMP messages that can be sent on a network. And IANA documents the various parameters. And you can check out this link. The code field. Many ICMP packets, such as ICMP Destination Unreachable, ICMP Redirect, and more, have a code field. And codes mean different things in different types of packets. And the checksum field provides error detection for the ICMP header. So types of ICMPv4 messages. There's many ICMP message types, but they fall into 2 general categories: error messages and informational messages. All ICMPv4 messages use a common message format and are sent and received using a simple set of protocol rules. So examples of some message types are destination unreachable and redirect. For example, destination unreachable messages are returned to the source node when a packet was sent, and it cannot be delivered to the destination. The sender can use that information to decide how they want to correct the problem. Also, source quench is a message used to tell the source node to reduce the rate of speed at which it sends packets to the destination. The source node can respond by slowing down the transmission rate until it stops receiving the source quench messages. So all ICMPv4 messages use a common message format. They're sent and received using a simple set of protocol rules, and they differ depending on the specific message type. So we talked about our source node and destination unreachable. We talked about source quench. Time exceeded. So time exceeded is sent in 2 circumstances: when a packet's time to live field is decremented to 0 by the routers on the network before the packet reaches the destination, and when some fragments of a message do not reach the destination node by the time the node's reassembly timer reaches 0. Redirect. So a first hop router sends an ICMP redirect message to a source network node to tell it that a preferable route exists, but really this isn't an error message. However, in ICMPv4, it's classified as an error message. So a parameter problem is a quote-unquote generic error message, and it can be sent back to the source by any device in the network when the device detects an error in any header field in an IP packet. So echo request and echo reply, this is the one you're probably all familiar with already. It's used for connectivity testing between nodes. This is used by ping, and it's the most common implementation of ICMP. Timestamp and timestamp reply. Routers use this pair of messages on a network to sync their system clocks for date and time. And time synchronization does not work very well in large networks because of the time it takes for ICMPv4 messages to travel back and forth. So the delay itself causes issues, which is pretty funny considering it is a timestamp message in order to sync time. But router advertisement and router solicitation allows the network node that isn't manually configured with the address of a first hop router to ask and receive information about routers on the local network. Address mask request and mask reply. Give hosts a method to determine their network mask. Most computers acquire this and their subnet mask via DHCP. For probably the second most common ICMP message that you have experienced but may have not known it was an ICMP message is Traceroute. It's similar to echo request and echo reply, but it traces the sequence of routers from the source to the destination going hop by hop by hop. Windows computers use Traceroute to send the messages, and Linux and Mac OS use Traceroute. So TraceRT, if you remember, there was an old meme on the internet, TracerT. That's Windows, but Traceroute for Linux and Unix variants. So ICMP structures and functions. Several ICMP packets have to send information in the ICMP portion of the packet, and it supports additional fields. The packet types include type 0 through 8, so echo reply, echo request, type 3. Sorry, 0 and 8, not 0 through 8. Type 3, which is destination unreachable. And there's others which have been deprecated in terms of variable ICMP structures. So we talked about 0 is echo reply, 8 is echo request. Those are two types, RFC 792. The identifier and the sequence field are used to aid in matching echo messages with echo replies. So echo requests and echo replies. So here is a diagram of variable ICMP structures and functions. And here's a capture of an ICMP echo request packet. And here is a capture of an ICMP echo reply packet. So type 3 is destination unreachable. So these packets are often used by network troubleshooters. They closely track ICMP destination unreachable packets. The host that sends destination unreachable has to return the IP header and 8 bytes of the original datagram that triggered the response. And there's a total of 16 possible codes currently assigned to the ICMP destination unreachable type number. And here is a breakdown of the ICMP destination unreachable packet structure. Here's a flow diagram of how it works. So ICMP packets with content from the triggering packet. Type 5 is a redirect. So routers send ICMP redirect messages to hosts to indicate a preferable route exists. An ICMP redirect packet is a 4-byte field for the preferred gateway address. And ideally, clients should update routing tables to indicate their optimal path. So types 9 and 10 router advertisement and router solicitation. So hosts send router solicitation packets, and routers respond with advertisement packets. And ICMP router advertisement packets include the following fields: the number of addresses, the address size, the lifetime, the first router address, the precedence level of the first router, router address 2, and that's router's precedence level. So type 11, time exceeded. Routers or hosts can send these ICMP packets. There's two codes that can be used: the time to live exceeded in transit, or that's code 0, and code 1 is fragment reassembly time exceeded. So when a router is acting as a host and assembling packets, it can issue a code 1 message. So type 12 is a parameter problem. It indicates problems not covered by the other ICMP error messages. So codes used in ICMP parameter problems messages: code 0, the pointer that indicates the error. Code 1 is missing a required option. Code 2 is bad length, and so on and so forth. We talked about timestamp and timestamp reply, types 13 and 14. They're defined as methods for IP hosts to obtain the current time. We talked about how on large networks it doesn't really work that well. The value returned is the number of milliseconds since midnight in universal time, so UTC. And ICMP timestamp and timestamp reply use the same structure. ICMPv6 provides the same basic mechanism for error reporting and information exchange between network devices as ICMPv4. The specs for v4 are over 30 years old, and a new version of ICMP is required for modern network messaging. ICMPv6 message types still fall into two main groups: error messages and informational messages. However, the message types in these categories have changed, some of them significantly. So ICMPv6 was originally spec'd as RFC 1885, which was made obsolete by RFC 2463. The current spec is RFC 4443, Internet Control Message Protocol ICMPv6 for Internet Protocol version 6 IPv6 specification. RFC 4443 was updated by RFC 4884, extended ICMP support multi-part messages. ICMPv6 is described as having message types and message types formats updated for use with the IPv6 protocol. So the various types of ICMPv6 messages: types 0 to 127 cover error messages, and types 128 to 255 cover informationals. But some message names are the same as their ICMPv4 counterparts. However, many of them are completely new. Here's a table of all the different types of ICMPv6 messages. And here's a continued table of ICMPv6 messages. So RFC 4443 describes the general format of IPv6 messages. Specific message types may have their own unique formatting beyond what's shown here in the diagram. An IPv6 header and potentially one or more extension headers come before the ICMPv6 message. The next header value for the ICMPv6 header is 58, and the immediately preceding header. So again, the figure here is just the general format of an ICMPv6 message header. So ICMPv6 error messages, again, the type values go from 0 to 127, and RFC 4443 defines those. We're going to talk about destination unreachable, packet too big, time exceeded, and parameter problem But there's other error message types that are reserved or unassigned or set aside for testing and experimentation. So destination unreachable messages, they're produced by routers or the IPv6 layer in the source node in response to encountering a packet that cannot be delivered to the destination. And when a router encounters this packet, it sends the destination unreachable message back to the source node. So when we talk about this, so we talked about packet can't be delivered to the destination. Once the source node receives the destination unreachable message, that node is responsible for determining an appropriate response. So one possible problem in this circumstance is, just as the source node's packet didn't reach its destination, the destination unreachable message may not reach the source node. So in the case that the source node will not know a problem has occurred, it's going to continue to try and send the packet to the destination node until it receives an error message. And the figure on this screen is the destination unreachable message format. Here are various destination unreachable message format fields. So the packet to big messages, it's a new ICMPv6 error message type. And it's required because of how IPv6 manages data fragmentation and reassembly. So in this diagram, we have the packet to big message format fields, so the type, the code, as well as the MTU. So time exceeded is really similar to time exceeded in IPv4. And the message format is identical to the destination unreachable message. So the values for the code field in this case, 0 for if the hop limit was exceeded, and 1 if fragment reassembly time was exceeded. So just like in ICMPv4, ICMPv6 parameter problem messages are generic messages as opposed to the response to a very specific error. It's sent to the source node when a problem with the packet has been encountered, and one of the packet's fields or parameters in the IPv6 header. So in this slide, we have a table of the various codes and the pointer. So type codes 128 to 255, again, are informational messages in ICMPv6. And these informational messages aren't used to report errors, but to provide information to the source node. So just like with ICMPv4, it does the same thing. It's not there to report an error. But it may do some testing, support, or diagnostic functions for the IPv6 network. So first example of a testing and diagnostic function, echo request and echo reply used by ping. It's specified in RFC 4443, and it's, again, a basic connectivity request. So in this figure, we have the format for the echo request and the echo reply messages. Next is router advertisement and router solicitation messages. So this is in RFC 4861. Router discovery function has been integrated into neighbor discovery protocol itself. So neighbor solicitation, neighbor advertisement messages are specified in RFC 4861 and are part of the IPv6 neighbor discovery protocol. The IPv6 network nodes send neighbor solicitations in order to request the link layer address of a target node and, at the same time, send the target node their own link layer address. So the neighbor advertisement message format, let me flip here. It's almost identical to the neighbor solicitation message format, except in the reserved field, there's 3 possible flags. The R flag is the router flag that, when set, indicates the sender's a router. The S flag, or the solicited flag, When that's set, it indicates the advertisement was sent in response to a neighbor solicitation message from the destination. And the O flag, O for override, when that's set, it indicates that the advertisement should override an existing cache entry and update the cached link layer address. Redirect messages are specified by RFC 4861 in the ICMPv6 implementation. Redirects were considered error messages under ICMPv4. The messages don't actually describe an error, but provide information to a network node it needs to change which router it is using on the local link to send messages to a particular destination. And here is a diagram of the redirect message format. Router renumbering for IPv6 is specified in RFC 2894, and it allows address prefixes on routers to be configured and reconfigured with the same ease of neighbor discovery and address auto-configuration for network nodes. This allows admins to update the prefixes used and advertised by IPv6 routers throughout a whole site. And here is a ICMPv6 router renumbering message header format diagram. So when we compare ICMPv4 and v6 messages, they perform the same basic functions. However, ICMPv6 provides added functionality. So common general message types between the two, connectivity checking, error checking, informational messages, and fragmentation required messages. But in IPv6, there's some specifically new messages that don't apply to ICMPv4. The address assignment messages, address resolution, multicast group management, and mobile IPv6 support messages. So next is PMTU. So PMTU discovery. In IPv4, it allowed routers to notify nodes using ICMPv4 messages if they need to change the MTU size of the packets they're sending via ICMPv4 messages. Each PMTU is made up of a number of links between the source and the destination nodes, and each link can have a different MTU size. The PMTU is the size of the smallest MTU for an individual link. So changes to PMTU in IPv6, MTU sizing and fragmentation were updated to improve efficiency and quality of sending and receiving network traffic. So one way this was achieved was by setting the default MTU for packets to 1,280 bytes. Another method was to eliminate fragmentation of packets once they've been sent from the source node. So IPv6 routers are unable to fragment packets in transit. If a packet needs to be fragmented in order to be delivered to the destination, the source node has to perform that fragmentation. The most common use for ICMP is testing and troubleshooting. And we've talked about two well-known IP utilities, which you've probably used, Ping and Traceroute, and both of these rely on ICMP to perform connectivity tests and path discovery. There are times when network troubleshooting and security are going to clash. One Cisco technician was trying to diagnose a problem on a switch. They were able to ping the switch, but when the switch could not ping, the technician's laptop, when commanded, for the console connection. So as an example, that tech realized they had the built-in firewall feature on his Windows laptop turned on, and the firewall was configured to block ICMP echo replies. So a lot of times, even though we have these useful tools, such as Ping, from a utility and connectivity testing standpoint, they can reveal the existence of hosts, for instance, or give an idea of the various hops required to get to a specific host in a valid connection scenario. And you might have to turn these off, which then degrades the connectivity testing functionality you need for the sake of security. So just remember, sometimes what we think of as a problem on the network uh, may be there for a reason. So ping again is a form of echo communication, so echo reply, echo request. It's a connectionless process. There's no guarantee of delivery. The client transmits an echo request, and upon receipt, the target echoes back that data. Here's an example of the ping utility in use. Most ping utilities send a series of several echo requests to a target in order to obtain average response time. And normally that's in milliseconds. A ping utility will send a series of 4 ICMP echo requests with a 1-second ICMP echo reply timeout value by default. It supports IP addresses and names and uses traditional name resolution processes. Um, Regarding the ping command line parameters, the -t parameter allows you to send an endless series of echo packets to hosts. The stream doesn't self-terminate though, so you have to use the Control-C combination to stop the packet stream from the utility. So here's an example of the ping utility we just talked about running on a Windows machine. And some various parameters, so -L for the size. You can specify time to live, -I, TOS with -V, -W with timeout. So again, play around with ping, and you can view the help file for information on all the various parameters. So Traceroute, the Traceroute utility uses route tracing to identify a path from the sender to the target. And remember, Traceroute is a TCP/IP utility. The Windows version is called TraceRT if you're typing it in. And on Linux, Unix variant, you'll type in Traceroute, the whole word. Available parameters, -D, -H for max hops, -W for timeout. So those are some of your switches. And here's an example of Traceroute using ICMPv4 to find the various routers across the path to the destination host. So Pathping is another command line utility, and it uses ICMP echo packets to test routering link latency, as well as packet loss, and it's been available in Windows since Windows 2000. So you can use PMTU discovery with ICMP. So it's defined in RFC 1191, and it enables the source to learn the currently supported MTU across an entire path without requiring fragmentation. So here is an example of PMTU discovery and how it automatically determines the PMTU of a path to make sure that there's no fragmentation required. So the process for that, host A sends a 4096 byte packet to host B. Router 1 discards the packet and sends back a fragmentation needed method. Host A resends the packet using maximum MTU size. Router 1 forwards the packet across the network to router 2. Router 2 forwards to network 3, and so on and so forth, all up until it arrives at host B. We look at an example. So again, we want to find what is the smallest MTU that we have to, or the largest MTU we can use without having to fragment. So routing sequences for ICMP, while routing protocols such as Routing Information Protocol or RIP and OSPF, if you remember Open Shortest Path First, they provide route information to routers. ICMP can provide routing information to hosts. So routers can use ICMP to provide a default gateway to a host if the host asks for assistance. Routers can also send ICMP messages called ICMP redirect messages to redirect a host to another router that offers a more optimal route. So IP hosts typically learn about routes through manual configuration of your default gateway and redirection messages. And they send ICMP router solicitations and router replies with ICMP router advertisements. So by default, the ICMP router solicitation packet is sent to all routers IP to the IP multicast address of 224.0.0.2. Um, Hosts that would not use router discovery again, either have to rely on the manually configured default gateway in the local computer or the default gateway that's sent through DHCP and the DHCP server that's handing out that information to hosts configured to accept DHCP network settings along with IP addresses, subnet masks, DNS primary and secondary servers, etc. ICMP router solicitation occurs upon boot with the computer sending out a router multicast requesting the IP address of the router interface and of the default gateway. So here's an example of hosts discovering local routers using the router discovery process. Some routers, so router advertising, some routers, they can be configured to send periodic ICMP router advertisement packets. The periodic ICMP router advertisements does not mean that ICMP is a routing protocol. It just allows hosts to passively learn about available routes. The default lifetime value for route entries is 30 minutes, and the advertising rate is between 7 and 10 minutes. So even though a router can send a message back to the host giving the IP address of a better router, it will still forward the originally sent packet to its destination. So here, we're seeing an example of redirection to a better router. There's a major drawback to redirection. Let's say your default gateway forwards your message to the next hop router. The next hop router may know of a third router that would be a better choice and sends the redirection message back to the sending host. The default gateway doesn't get this information, and while the host can then amend its routing table to include the third router, the default gateway will still be unaware of this and can continue to send packets through the same next hop router it began to use. So security issues for ICMPv4. We talked about this before. ICMP, we can use it as a footprinting tool or an information gathering tool. A lot of individuals and organizations want to limit the amount of ICMP traffic that flows through networks. Because again, you can use ICMP not only for discovery, but for denial of service attacks. You can flood a gateway server or a router with a huge amount of ICMP packets, or even oversized ICMP packets, which the attack is called the ping of death. In order to either flood the memory buffer or cause a slowdown on that gateway server or router or other piece of equipment. Um, so it's ICMP has been a huge problem, and oftentimes it's simply just disabled. In terms of discovery, once someone knows the various addresses on a network, they can use it to continue vulnerability scanning or other footprinting techniques to gather information for a potential attack. So an ICMP redirect attack, ICMP can be used to manipulate traffic for the flow between hosts. An attacker can then redirect traffic to their machine and perform what are called man-in-the-middle style attacks, when they sit between a source and a destination and either read data, exfiltrate data, or modify data. ICMP router discovery. It's a protocol specification that's susceptible to attack on a local network. So during the discovery process, a router solicitation message will find its way to an attacker's machine, and the attacker spoofs a response back to the target. Because no authentication is performed, the recipient doesn't know if that response is real or not. Inverse mapping is another example. When a filtering device is detected between an attacker and a potential target, so an attacker interrogates the routing device, so it intentionally sends packets to unused or vacant network addresses, and then upon receipt of a packet destined for a non-existent host, a router passes it on because ICMP is a stateless protocol. Once a packet reaches an internal router, the router replies with the host's unreachable message for bogus entries, and then an attacker can deduce using that information which addresses correspond to a live target. Firewalking is an example of another type of attack. So it's a two-phase attack using Traceroute to discover a hop count to a firewall. And once a filtering device is identified, the other wave of the attack is sending a packet with a time to live of one greater than the final hop. And the goal there is to elicit a time exceeded response from beyond the firewall to indicate a live or responsive target. So we want to find what's behind the firewall. We can increase that hop count by 1 and use ICMP in order to discover those potential hosts that can then be scanned further. Security issues in ICMP, they exist there too, but there's built-in security features in v6. It's designed to prevent attacks sent from another network segment. So there's features such as value in a hop limit field being sent as 255. The source address of ICMPv6 packets either have to be link local or unspecified. Authentication for v6 packet exchanges is managed using IPv6 auth or IPv6 ESP. And then ICMPv6 is also protected by IPsec. When we're decoding ICMP packets, we want to examine the ICMPv4 packet format. So generate the ICMPv4 traffic in the form of an echo request and response using the ping utility or Traceroute for Traceroute and Windows. Again, Traceroute in Mac OS, Linux, and Unix flavors. And use a tool such as Wireshark to capture and decode ICMP packets for examination. So here is a captured ICMPv4 echo reply packet. And we can compare that to the known format fields for echo requests and echo reply messages. And here's an ICMPv6 echo reply packet. And we can compare them to their v6 echo request, echo reply message format fields. So in summary, ICMP gives you vital feedback about IP routing and delivery problems, and it's really part of IP itself. The support is required in any standard compliant IP implementation, and it's used by ping and Traceroute to measure round trip times and do path discovery. It also supports PMTU discovery between a sender and receiver. Route and routing error information from ICMP derives from numerous types of ICMP messages. ICMP also supports route optimization through ICMP redirects. But remember, security issues are super important, and message structures and functions can vary. ICMPv4 and v6 echo messages have a very similar format.